welcome to this course on FPGA based signal processing systems. We'll continue with the sequential logic circuits. As we had seen in the previous lecture, that in sequential circuit consists of a combinational circuit and a memory element. So this memory elements can have the clock, and consider this element as a bistable element here, which is having the two inverters that is shown over here. The input of one inverter is suppose voltage input 1, and the other one is voltage input output 1, the output, and the next inverter whose input is V in 2 and the output is V out 2. So the Q and Qn is it doesn't have take any input, the outputs are Q and Qn. So the if supposing this V input is 0, V input is 0, the V output 1, V input 1 is 0, then V out 1 is 1. Okay, so if this is 1, then this V in 2 is becoming 1, it is back to back connected, okay, and the V out 2 becomes 0. Okay, so here you have one output which is Q is 1 and another output Qn which is complement of it. So there are two stable states. So we normally in the flip flops and the latches we have these two stable states. This can be even characterized with the diagram, whereas this is taking as V in and this is V out. So this can be V in 1 and V out 1. So for certain level of V input 1, that is okay. So the output will be output and input relation is this. So if the V input is less and the V output is going to be high for a particular level of inputs, suppose for a 0 to 5 volt input, this can be for 0 to 2, this is going to be 1, and in between similarly for certain range from here to here, the output the higher output of V in may be 3 volts to 5 volts, it is going to be the logic 0. So this is logic 1 and logic 0. So when you consider input, this part is low and this part is high. So this can be even considered with another case for the another inverter. That means this portion is high when this is low. Okay, so and this stable, and this portion is here compared to this input, this is stable. So this let us take this input the output here, and the first case, these are stable ones, two stable states. In the flip-flop latches, in the sequential circuits, we have these two stable states. So apart from that, we can have the one more the point, which is the another equilibrium point. These two are the two equilibrium points. Another one is the third equilibrium point, where in which this is called the metastable state. So it has to, if you give a particular input to the device, then it has to cross over from one, suppose logic 0 to logic 1 through this, or from 1 to 0. If you give 1, it has to go to the 0. Okay. So in this state, metastable state, what happens if there is no sufficient input is given to the devices, then it would get into the metastable state, and the output will be Q may be not either 0 nor 1. So it will be oscillating between that 0 and 1. Okay, so it will go 0 and 1, 0 and 1, and so on. The noise in this circuit, for noise also can create that. If there is no sufficient noise in this, it will not move the device to the one stable state here to here or here to here, but it is lying in between, that is between 0 and 1. So just an illustration to understand this what is the metastable state, which is also is a state of the these devices. This is in terms of analog, not digital, but this the logic what we take is initially this is for particular voltage, the logic 0, and this rest is for a set of another voltage, it is going to be 1. So logic 0 and logic 1 is for digital circuits, it is defined that way. And considering the D flip-flop, now the functional table of the flip-flops which we had seen, also the function, what is the functional table and what is the characteristic equation. So the characteristic equation, we had seen the next state of the flip-flop is purely depending on the D input. So whatever is the change in D is reflected to Q if the clock at the clock edge. Okay, so the functional table, if you take them, D is the input, and if it is a positive edge triggered flip-flop, this is showing the positive edge triggered, that Q becomes 0 because D is 0, Q is 0, and then Q bar is 1. So similarly, when the D input is 1, at passage this becomes 1. This is call it as functional table of the D flip-flop. And the excitation table, which also is needed for the conversion of one flip-flop to another and so on. Suppose you have the D flip-flop, you want to use it as a T flip-flop or JQ flip-flop, what should be the scenario, and how do we do that? So it's a very, so the excitation table of this is necessary to do that. So according to the characteristic equation, what is given here, Q star is D. This is understood from the functional table. Now coming to this, if Q is the present state and the Q star is next state, and the Q is initially this is present is 0, and then it becomes it is also 0 in the next state. Okay, there is no change in the Q. That means the D input was 0. There is no because D will be transferred to 0. So, and the similar last state was this present state, that is Q is 0 and it is changed to 1. That means the input was 1. D input was 1. The input D flip-flop input was given 1, so the next state has become 1. Similarly, if there is any change from the 1 to 0, so the next state is 0. So there is a change. So, but the input, what was the input, it should be 0. Okay, and if there is, it is staying over there, D equal to 1 is 1, and then that 1, because this next state is 1, this is 1. Okay, so whatever this next state will be, that is depending on D, that is, this is clearly signifies that. So D input, what was given, is next transferred to Q star irrespective of this Q. So the JK flip-flop, similarly, the characteristic equation is Q star is JQ dash and K dash Q, it's known, and its functional table J and K is positive edge triggered pulse. Here is the clock, and then the J and K are 0, 0. The Q is last Q and last Q bar are maintained. Okay, the 0, 1, then Q takes Q 0 and the Q dash is 1. If it is 1, 0 and the Q takes 1, so that because of that it becomes 0. So 1, 1, that this is getting complemented. Q dash, this becomes last Q dash and last Q. Okay, so this is functional table, and the excitation table similarly from this, what was the Q and Q star, the present and next states of Q, and the inputs J and K. What was the input applied so that this next state is 0? Okay, so present state is 0. From 0 it is changing to 0. That means it is in the same state. Then J is 0 and K can be anything. So that is either it is 0 or 1. In that case, it is Q star is next state is 0. So similarly, if J is 1 and K can be 0 or 1, in that case also next state become 1. So it's coming from over here, and if K is 1, J of unknown 0 or 1, so this is next state is 0. So K is 0, X is 1, this becomes 1. So the changes of the present state to next state can occur in this way. So this is the excitation table, which is used again when you convert one flip-flop to the another. So T flip-flop, the characteristic equation, it is complementing the last state. Q is getting complemented. Okay, so at the clock edge, when T is 0, the last Q is maintained in the functional table, and if it is 1, and then it will be complemented. So the excitation table comes from, so whenever there is a toggle 1, there will be change in state, else the same state is maintained. This is the same state. Q present, the next state will be same as the previous one. so whenever toggle is 1, then it is getting complemented, characteristic equations which I have given. So based on this, how do we convert this? Suppose we have already in the modules D flip-flops, okay. All the D flip-flops we have coded, the Verilog modules, D flip-flop with asynchronous reset, D flip-flop with synchronous reset. So can we use that D flip-flop to as a T flip-flop and design some other sequential circuits? So in this step, what we try to do is that, so what is the flip-flop we are going to convert? That is, I want a T flip-flop from D flip-flop. So T and Q, what should be the Q? So make the two inputs. Okay, the two inputs can have different combinations. So that is 0 0 0 1 1 0 1 1. Write it down. And what would be the next state? Okay, so what is the next state of this in this T using here? So use to make from here to here. Let's say this T. Use this functional table of the T flip flop. Okay, so T flip flop, the next state is 0 here because this is 0. The next state is 0. Okay, and T is 0, and the next state is also doesn't change. This is just maintain the previous states. So T is 1, so this is getting complemented, and T is 1, this is getting complemented. So this is using the functional table of the T flip flop. Now coming to the D flip flop excitation table, what should be the input when present state was this and the next state was this? Okay, so there is no change. That is, I mean, the next state is now 0, so that means the input should have been D 0. Next state is 1, and the next D should have been 1. Next state is 1, D should have been 1. Next state is 0, so this is D should have been 0 here. So using this excitation table. So functional and excitation tables are being used for this conversion. And let's take this K-map. For that, T and Q are taken in the cutoff map 0 0. When T and Q are 0 0, the output is 0 here, and when it is 0 1, this is 1, and 1 0. Similar, this is 1 1 1, and it becomes 0. So we take this distinguished ones. So we get T dash Q, this plus T Q dash. Okay, D is this. So if we have the D flip flop, let's take the clock edge D flip flop, and this is Q, and this is QN or Q dash, whatever you call it. Then we have this Q. So now this D should be given the logic T dash. Okay, so let's take this T is available with here, this T dash, okay, and Q, and the T and Q, this can be taken as an XOR gate. Okay, so one is T and another one is Q. So take an XOR gate, and you have this T, or let's take this is T and this is Q, just to connect it back. Take this as T, okay, and here is let me take it the XOR gate. So this is the clock. You can have reset, or this is, you can also have the reset, synchronous or asynchronous reset. So the D flip flop with module will be using it as a T flip flop for the other sequential circuit design, synchronous sequential circuits we will be designing, so that the D conversion into T. Okay, so now with respect, if T is 1, the toggle, the output gets toggled, otherwise the previous state is maintained. So this is for the D to T flip flop. You can similarly convert any of this, any flip, T to D or SR to D or JK to D and so on. So that's possible using the functional and excitation table in this manner. So let's have this D flip flop with non-blocking statement also, and then we'll move on to the simulation. So module, we have this D flip flop with a non-blocking statement. Input clock, input is D, and output Q and output QN. So this is a D flip flop. Reg Q and Qn because it is used Q and Qn are used in the always block. Always at passage of the clock begin. So the non-blocking statement, you can say, so far we were using the blocking statement. D is will be assigned to Q, Q less than or equal to D, and Qn less than or equal to tilde D, okay, and end. Okay, so what is the difference between this this flip flop and the previous one which we had done? We have just had this equal to sign. Okay, here we have the less than or equal to sign. Okay, here the D, whenever there is a passage of the clock, D is evaluated. Okay, that means D whatever value, and it is not assigned immediately to Q, and tilde D is evaluated and it is not assigned to Q and immediately. So within the always block these are sequential. The one statement at that time, D is evaluated not assigned, D tilde is evaluated not assigned. So after this evaluation, all the assignments are taking at the current end of the current simulation time. So D will be assigned to Q and tilde D will be assigned to Qn after the at the end of the current. Suppose it is evaluating at the passage of the clock, that at current simulation time end both will be assigned to it. Okay, whereas if it is blocking statement, D is evaluated. Suppose it is Q equal to D and Qn equal to D tilde. D will be evaluated and assigned to Q, and D tilde after that, after assignment, that means Q is getting the D value immediately. After that, D value, D tilde, that is evaluated and assigned. So it is an immediate assignment, here is a late assignment. So in this case it is evaluated not assigned, and T tilde is also evaluated not assigned at the end of the current time, that is after this execution. This both, this Q and Qn will be getting the value. So the difference we will see in few examples also, that just introducing in the flip flop we can use the non-blocking statement also. So here if you use this Q, if you use Q here, then it will take this for evaluation of this, it will take the old Q value and then make the Qn. Okay, so so that won't be, so it's tilde D we had given here, the is given in the code. So test bench module name reg clock D, and outputs are Qn. So instantiate that module with non-blocking statement dot clock D, Q and Qn. Also the initial begin, let's see the display, we use it in all the test benches. Also the monitor, initialize the inputs, generate a clock, next hash 100 clock equal to not clock, then comes the initial begin. We have the stimulus hash 100, D is made 0, D is equal to 1 after 100 nanoseconds. After 300 D is made 0, and after hash 200 1 bit 1 D. N. So let's see that in the waveform editor how this is working here. So we have the clock, that it's again the D flip flop, just the only change is the non-blocking statement. So the behavior should be same, the D flip flop behavior should be same. So the clock is 1 0 1 0 here, and look at the positive edges of the clock, passage of the clock. So what happened is D is 0 initially and D is 0, okay, so that Q is becoming 0, no reset is used over here, and D is changing here, but this last value will be maintained till this point, and at this point it is 1, yeah, it is transferred here, okay, at this point it is 0, so yes, you are getting it, and there is no change in the behavior of the that code what we had, 1 is here, okay. So this is the same D flip flop we have used. Until 100, it is giving some value, unknown values. 100 nanoseconds D is 0, so it is passed to Q, and then it is retained. It is passed over here at this 300 and maintained. Here at 400, this data is changing, but still, sorry, clock is made negative, but data is same. So data anyway it is sampled at this point only. So here 600 and then 700, the clock is 1, and the 900 the clock is 1. So clock is edges. So this is the output printed in the console. So it's with non-blocking statement. The behavior is not changed now, and then we will see them in the synthesis process, and a few more example how with the time delay involved in this, delayed assignment, delayed evaluation, and so on. So how does it make a difference? Okay. Now the T flip-flop, that we had have this D flip-flop module, and converted that to T flip-flop with an XOR function. Q is made fed back to the XOR input here, and T is, if T makes 1, T is 1, then it keeps toggling the date. It keeps toggling. So clock is available. So let's see the behavior of this circuit. So the input and the module have this input T flip-flop, module name T is the input, clock here, reset is the 1, and then we have this output Q and the Qn as well. Close the bracket with semicolon. So here you can see that include with the compiler directive, give the full path of the D flip-flop asynchronous reset code. We are going to use it in this T flip-flop instead of this block. Okay, so this block is instantiated using the DFFAR code. So wire DT, this means this will I'll tell you what is this DTT. Assign DTT equal to Q XOR T, instantiate the D flip-flop over here. So this is the DT here, this point, the DT is this. This is giving the Q and T are XOR, and assign DT equal to Q XOR T. Okay, so we have the D flip-flop and we have this XOR gate, XOR function DT. So this needs to be connected. So here we have declare these two are connected. So we declare this as wire in the as in the case of structural model, like it needs to be declared as wire DT and assign. So now the continuation of the D flip-flop description. Instantiate the D flip-flop DFFR, that is the name of the file module name, that is we used the D flip-flop asynchronous reset, and the optional module name here DT. So you can see that this is DT, the D input. In this here, D was the input, and then reset, and then clock, and Q and Qn. This is the order we have used in the previous DFFR model. So this is nothing but D input to this. So that is obtained by taking the Q and T XOR DT. So simple instantiation of this module. This is over here, and assign this XOR gate, two of them. Okay, so anyway, this is the D flip-flop instantiation was done with the always block. Okay, so now this to Q and T gives the DT output. Wire is this should be declared as wire here. Okay, so there is no other declaration like reg, because those are covered in the D flip-flop asynchronous reset module. Now the test bench goes to module D flip-flop and the test bench module. The inputs reg T, that is T which is should be given to the given as input to the T flip-flop, and the clock reset asynchronous reset which is in the D flip-flop, and output wire Q and Qn are the output. Instantiate that now T flip-flop which is TFF UUT, which has the T, clock, reset, Q and QI. Okay, so you can see this T flip-flop is the module. Just now we had written that Verilog module D flip-flop, which instantiated the D flip-flop inside, and the initial begin So initialize the inputs T0, clock 0, reset 0, and here is, this is the initialization. Just display and monitor the inputs and outputs T, clock, reset, Q and Qn. So initially after 10 nanosecond, make the reset 0 and clock is 1 and T 1. So reset 1 and then T equal to 0, reset 0 and T1 and end. Okay. So with this we have the clock, generated clock, always #50 clock equal to clock naught. This can be done with the initial also, initial block, or it can be with this block after giving the stimulus as well. So anyway, these are concurrent, so the order in which it is written doesn't matter. #50 clock equal to clock naught. So now the outputs, let us see the output in the viewer, waveform viewer. The clock which is having, so here it is not okay, 0, 1, 0, this is 1, 1, 0, 1, 0, 1, like, and these are the edges. Okay. Initially clock is made 1 sometime with irrespective of that, that is why it is showing 1. And let's take the here also, this is reset 1 and reset 0. So let's take this one and then we'll come back to the rest of that thing. So at the passage of the clock, reset is 0, so the T is 1. Okay, so now Q is made 1. Okay, so T is previous state was 0 Q and it is toggled to 1. Okay, and next is here T is 1, continuously made 1. So the Q1 which is 0 is made 1 in this clock edge. Next at this clock edge T is again 1. So this is complemented to 0, 1, 0, 1, 0 every, because T is made 1 all the time. So in all the clock edges you can see passage of the clock, this is 1 and 0, 1. Okay. So anyway, this complement is going to be, Qn is going to be 1, 0, 1, 0 and so on. Let us look at here that reset 1, the T is 1, so the reset is 0 here, and because it was a preset, Qn bar doesn't give any output, this is unknown value. So though the reset is 1 and the clock is 1, the reset is 0 and the clock is 1, it doesn't take the global reset time during the global initialization. So the clock is started over here and then reset made, and then so at the clock edge, so it behaves like a T flip-flop. So the T flip-flop complements the or toggles the Q. Okay, so when T is 1, so T is 1, the previous state, that Q is getting complemented. This T flip-flop can also be used in the for suppose this is the 100 nanoseconds clock period, 50 and 50, and you can see the total time period of the Q, which is 200 nanoseconds. So 100 nanoseconds clock and Q has become, the time period is 200 nanoseconds. You can use it for the clock divider. Okay, so this time period has become extended, the clock is becoming half. Okay, so the T flip-flop can be, if you give T equal to 1 and allow it to toggle its output, then you can generate a clock divide by 2 clock from the T flip-flop as well. That's one also can be used in other applications. So the same thing can be viewed in the log file as well, 200, 300 and 500 nanoseconds. So up to this, there is the output is unknown, and here at 500, so 50, sorry, 20, 30 and 50, and here is 60, and so it is going to be active at 50, 1, 0, T is 1, so reset is 1, these cases, and Q and Qn, Q is 0 and Qn is 1, this part. Okay, and then after this it is becoming, the reset is 0 and it is maintained over here. Same thing maintained over here. It sees a clock edge at 100. Okay, at 100, Q is Q, can see it is complemented from 0 to 1, and again it is complemented from 0 to 1, 1 to 0, and then again 0 to 1, so on. So the complementing behavior of the D flip-flop could be observed, which is using the D flip-flop. So you can build a larger modules from this D flip-flop and then make the T flip-flop and use the T flip-flop and design a counter or the asynchronous sequential circuits. This could be used. So this is one example of the instantiating one module in the sequential circuit, instantiating the D flip-flop and building the other flip-flop. So this is a list of the outputs for the 400, 450, 500 and so on, and you can observe the change in the Q also. So with it we've just given the functional table, excitation table of a few flip-flops which we will be using in this course, and how do we convert one flip-flop to another, and instantiate the smaller module, the module which you had used initially. That same module can be used to build the larger modules in the Verilog, and we'll be building this DT and using this T with some other sequential circuits as well. Thank you.